thanks everyone for joining me today. Excited to be here to share a little bit about the James Webb Space Telescope, or as I will use for most of today, JWST, because it is ever so slightly shorter. To create today's presentation, I was able to utilize the same software we use in the dome here at the museum. It's planetarium software called Digistar 6. So yeah, we're going to be able to jump all over the universe, and we'll have a little bit of fun. So you're looking right at JWST now. That is the spacecraft that today's whole talk is going to be about. One of the biggest stories in astronomy in definitely the last month or so. But really, the idea has been around for decades. Let me do a quick introduction to the spacecraft for you. First, on the side that we're looking at right now, the kind of square-shaped section in the center of your screen, that's just called the spacecraft bus. And I probably won't mention it again throughout the rest of the presentation. Then there's this big diamond-shaped section that's called the sun shield. And on the other side of the sun shield, we have the telescope assembly itself. That's the mirrors. The big one is called the primary mirror, and the one sticking out in front of that is called the secondary mirror. And then behind the primary mirror, there is a little box where all of the instruments are stored. So some of those sections will be important during different parts of the presentation. So in our current view here, sun shield at the bottom, above that, the telescope, secondary mirror off to the right, instruments on the left. And now that you know the basic layout of JWST, I thought another important little bit of information to share with you would just be the scale of this telescope. JWST is often compared to a tennis court, and it happens to be a pretty good comparison. If you've been in the dome here at the museum, that sun shield and its long dimension from front to back is right at 70 feet long. So it also just barely fits inside the dome. The dome is 76 feet in diameter. So you can kind of throw out the outer aisles, the stairs on the outside of the theater. That's about the length of JWST. So this is a pretty big spacecraft, pretty impressive. And just for another little bit of context, with the Olympics about to start, since I don't know, it's pretty cold, probably not playing tennis right now. Turns out not a lot of winter sports are played on courts of this size. But if you're watching the Olympic hockey games in the coming weeks, it's similar to the neutral zone in an ice rink. So that's about how big the observatory is. But one of the big challenges for JWST is its size. This thing is the size of a tennis court, but nobody in the world has rockets that can send things the size of a tennis court into space. In fact, the rocket that launched JWST about 40 days ago now, is December 25th, Christmas morning, was the Ariane 5, and its diameter is about 5 meters. It's about the size of the service box on a tennis court, the smaller box close to the net. So how do you get something of the size of a tennis court on something much smaller than a tennis court to get it into space? The answer turned out to be folding it all up into a much smaller shape. So the telescope that we have in space today is not exactly the telescope that launched from Earth. It's gone through some major changes. As JWST was designed, built, and tested over the last couple of decades here on Earth, they planned very carefully to make sure this whole observatory could be folded up to fit on the rocket for launch. So the mirrors folded up, that sun shield folds up. Everything had to be designed with exacting precision, because once you get it out in space, nobody is there to help it unfold again. So that was kind of that's the most complex part of JWST. There were 344 individual points of failure once they got into space that had to be retired so we can actually get a working telescope in the end. So you fold up the whole telescope. Then the final testing was done at Northrop Grumman's facilities in California. So you load it up on a boat, you ship it through the Panama Canal, you get to to Kourou in French Guiana. That's the European Space Agency's launch site. You put this telescope, which has to be all unfolded, has 344 individual points of failure. Everything has to work with exacting precision. You launch it into space on a rocket, which famously does not guarantee a very smooth ride. A couple of minutes of very intense vibrations, another 6.5 minutes of moderate vibrations until you're finally in space. And that whole process that was rehearsed here on Earth, that unfolding of the telescope, has to happen again, perhaps appropriately for a telescope it launched right into some clouds. But you get past those clouds, you're in space, you separate from the rocket, and everything unfolds. This took about 2 weeks for JWST, and it happened exactly in the sequence you're seeing here. It's an animation from NASA. So you get the solar panel, the antenna unfolded, then that sun shield has to unfold again, and then the mirror unfolds, and then you've got a telescope. And the telescope, I think, is going to be able to do some pretty amazing science. But one question I might have, I don't know if anybody has put it in the chat just yet. Why go to all this trouble? Why take a telescope, make it bigger than any of the rockets we have on Earth, fold it up so it fits on one of our rockets, unfold it in a very complex process? Why even bother with all of that? Well, JWST has sometimes been referred to as a replacement for the Hubble Space Telescope, or perhaps a successor to the Hubble Space Telescope. In a way, that's an okay description. I might just call it the next logical next logical step in space astronomy. To make some sense of that statement, we should probably compare JWST to some of its predecessors. Let's start with the Hubble Space Telescope. So I'm going to do a little side-by-side comparison here. We're going to have the Hubble Space Telescope on the left and JWST on the right. At first glance, these are obviously very different machines. Not so different in size, I suppose. Hubble Space Telescope would do okay at filling a tennis court, though its main structure is sometimes compared to a school bus instead. One of the big differences is what these telescopes can see. The Hubble Space Telescope observes primarily invisible light. The James Webb Space Telescope is an infrared telescope. So they don't immediately look like JWST is going to be a replacement for Hubble just yet. But before we can unravel all of that, since JWST is kind of the new kid on the block, everybody's paying attention to that. Let me remind you of some of the history and details of the Hubble Space Telescope. So let's focus on that one for a little bit. As I mentioned, this is a visible light telescope. I might call it an optical telescope at times as well. That means it sees primarily the same portion of the electromagnetic spectrum as our own eyes do. The electromagnetic spectrum stretches all the way from gamma rays out to radio waves, but our eyes and most of the instruments on Hubble are designed to see this narrow wavelength band that we call visible light. Hubble is a little bit sensitive just beyond the purple and red ends of our rainbow, and ultraviolet and infrared respectively, but primarily an optical telescope. Its big advance then is not so much what it sees, it's where it is. It's that second word in its name, space, that is so important here. I mean, think about the things that really trouble astronomers on Earth. Clouds, rain, bad weather in general. And then whenever you see a twinkling star in the sky, that's because of the motion of gases in Earth's atmosphere. That turbulence blurs every single picture we take with telescopes on Earth. So you can take some pretty dramatic steps to get around that with ground-based telescopes like adaptive optics and things like that. Or you could simply send your telescope into space. That may seem like a wild idea of the space age, but It's kind of an old idea. The idea of putting a telescope into space is at least 100 years old. Perhaps the first published suggestion, this is a good idea, dates to 1923. Hermann Oberth in the Rocket to Interplanetary Space says, yeah, you just put a telescope above Earth's atmosphere, you avoid all of these problems. Um, Astronomers were on board right away. One of the early proponents was American astronomer Lyman Spitzer. And he may not be the most important character in the story, but you're going to hear the name again later, so I wanted to mention it. Perhaps the most important character in the Hubble Space Telescope story is pictured here. Not the guy on the left, he walked on the moon, but for the Hubble Space Telescope, one of the most important figures in history is the woman on the right here, Nancy Grace Roman. She was NASA's first chief of astronomy. And when the space agency was brand new in the 1960s, she was already bringing together the engineers and scientists that would develop the plans that evolved into the Hubble Space Telescope. Though from the 60s to its launch, it didn't evolve all that much. Kind of surprisingly, you can find pictures of Roman from the 60s with models that are obviously the Hubble Space Telescope. So she's sometimes called the mother of Hubble. She really guided the program through its development in the 60s and 70s. It is funded by Congress in the late 70s. They began construction of the telescope. Got a couple of images of that. Here is the primary mirror of the Hubble Space Telescope, so comparable to Webb's big gold mirror. Here it's being ground into shape. Assembly of the telescope here. The top part is where the mirror is mounted at the back. The secondary mirrors out in the front. The bottom section here you see in the bottom right is where the instruments are going to go. Then the Hubble Space Telescope is loaded onto the Space Shuttle Discovery in April of 1990, launched into space. You're above the atmosphere now, and pretty famously smooth sailing from there. Okay, not quite. That mirror was ground into the wrong shape, so it was impossible to bring the telescope into focus. One of the earliest images is seen on the left here. It's blurry, nothing they could do about it, but Hubble was designed to be visited by astronauts. So the first servicing mission installed some corrective optics. Future servicing missions continued to improve and update the telescope. And although it hasn't been visited by astronauts in more than a decade now, and some of its instruments or more its computers are starting to show their age, Hubble is still doing okay. It's still an amazingly powerful instrument. It's doing valuable science, and it doesn't so much need a replacement. But there are limits to what the Hubble Space Telescope can see. And those limits can be traced back to, well, the telescope's namesake, Edwin Hubble, another astronomer from about 100 years ago. In the 1920s, he helped us figure out that the universe is expanding. The way that looks to us in the Milky Way, let's say that's the galaxy right in the middle of your screen here. Every direction we look, it appears that galaxies are moving away from us. Looks like everything is moving away from the Milky Way in all directions. That is kind of an illusion that we're at the center of everything. If I shift our focus here to a different galaxy, issue exactly the same command to make my model universe expand here, the result on your screen is the same. There's one galaxy in the center of your screen that does not appear to be moving. Everything else is moving away from it. So that's the expansion of the universe. It has another interesting effect, the light from distant stars and galaxies. As that light travels through the universe, it gets stretched out to longer wavelengths. Longer wavelengths are towards the red end of the visible rainbow. So we call this redshift. And that means that the most distant stars and galaxies, the very first ones to form in the universe, their light has been stretched out to the point where it's now invisible to optical telescopes like Hubble. So that's the reason to stretch our vision out into the infrared part of the spectrum. You can capture longer wavelengths, you can see more distant objects, you can see farther back in time. And that's kind of one of the superpowers of infrared astronomy. So that is one of the motivating factors of building this very complex telescope, launching it into space in the form of JWST. But JWST is not the first infrared space telescope. It's got some predecessors, like here, this little one was part of NASA's Great Observatories program. It was launched in 2003. It is the Spitzer. Space Telescope. Spitzer was shut down a couple of years ago, largely to free up people's time and money to pay for JWST. But Spitzer, did about 15 years of wonderful infrared astronomy, and because the European Space Agency is one of the partners on JWST, I'll add their most recent infrared space telescope, the Herschel Space Observatory, to our story here. So these two telescopes are able to observe infrared light, and that means they've got superpowers like seeing extremely distant objects. Infrared light can also travel through clouds of dust. So telescopes like Spitzer and Herschel and Webb can all witness things like the formation of stars, the formation of planets. They can track the formation of stars over vast swaths of time. So they can see how galaxies have evolved and changed over the history of the universe. You can split the infrared light into its component wavelengths and do something called spectroscopy. Then you can track individual molecules across the universe. You can say track water in star-forming regions or in the atmospheres of planets. One of the Spitzer Space Telescope's famous discoveries was this new ring around Saturn. It's made of dark dust that optical telescopes can't see, but it's visible in infrared light. One of Spitzer's most famous discoveries is probably the 7 transiting exoplanets around the red dwarf star TRAPPIST-1. Some of these planets are going to be great targets for JWST to search their atmospheres, if they have any, for molecules like water or oxygen or methane that might hint at a habitable atmosphere. But one of the most important images in infrared astronomy I can show you is this one, at least in my opinion. And if you know anything about the way I put shows together, you've probably already guessed that that is a picture of an asteroid. Now, asteroids have been important in our history here on Earth. And so you've got 2 asteroids of the same size. One reflects a lot of visible light, one doesn't. To our eyes and to optical telescopes, the brighter one might, look a little bit bigger. We might get tricked into thinking the darker one is smaller, or we may not see it at all. Similarly, if these asteroids are different sizes, if the bright one is small and the dark one is big, they might in total reflect the same amount of visible light. So to our eyes or to Hubble, they might look like they're the same brightness. We might think they're the same size, even though if they were on a collision course, that dark one would be much more dangerous. But you're probably most familiar with infrared light as, thermal energy or heat. So infrared light from things like asteroids are going to be light that it absorbs and emits again as heat. So asteroids can't lie to infrared telescopes. In infrared astronomy, we can tell directly how big these objects are. So you add that superpower of being able to tell how big things are to the spectroscopy that lets us track molecules across the universe. The ability to see much more distant and much older objects really makes infrared astronomy a very powerful tool to be able to understand the universe and its history. And so that is why JWST is so important. It has all those superpowers like Spitzer and Herschel had. It fills a small gap in our space telescope's coverage of the electromagnetic spectrum there. This image was originally from NASA, and they kind of stretched out the scale. So the gap between what Hubble could see and what Spitzer could see is pretty small, but Webb will cover that gap. And the real benefit here is that JWST is big, as I started out by showing you. One of the most important features of any telescope, like Hubble or Webb or Spitzer or Herschel, is the size of its primary mirror. This determines how much light it's going to be able to gather and direct to its instruments. JWST's primary mirror, much bigger than Hubble's, which was about the same size as Herschel's. And each individual segment of JWST's mirror is larger by itself than the primary mirror in Spitzer, which is that little tiny circle that you may not even be able to see over on the right. So with JWST, we're taking infrared astronomy, our ability to do it in space, and we're turning that ability up to 11. So that is why this should be a pretty neat mission to watch. So that background in mind, how are things going The telescope has now been in space for almost 40 days. It has arrived at its destination, a point almost 1 million miles away from the Earth, near a point called L2. Jim, this would be a great time to add those links into the chat to make sure everybody can see those. NASA is tracking conditions on the telescope, and you can follow along as well because infrared light is tied to thermal emission and heat energy. It's very important that the mirror and instruments on Webb are very cold. So that sun shield, the tennis court size sun shield, is there to keep the mirror and instruments in the shade, and that helps their temperatures get very low. So I've got their current temperatures on the screen for you here, and you can follow along on NASA's Where is Webb website, and you can see how those temperatures are going to be changing over the coming days, weeks, and months. The temperatures should all, on the cold side, eventually get down to similar to the surface of Pluto, but we're keeping Webb pretty close to the Earth so we can remain in constant and easy communication with it. That's because it's at this special point called L2. And as we wait for the telescope to start generating its scientific images and for the flood of data to start coming in, I thought for the rest of today's presentation, I'd focus on a couple of the more visible features of the mission. We'll explore the story and background of Webb just a little bit. So let's start with L2 and what this thing is. It's an example of a Lagrange point. And your first question is probably going to be, what is a Lagrange point? Well, not to worry. I've got that answer for you in a little segment that we're going to dive into now. Today, on Great Lagrange Points of History, we're going to just cover all of the Lagrange points. Lagrange points are an idea that were found out by an Italian mathematician in the late 1700s. His name was Joseph Louis Lagrange, so we call them Lagrange points. It's a solution to the three-body problem, and it's something that works in a rotating reference frame. So I'm going to get everything on the screen spinning for you there. It turns out that when you have a couple of objects in orbit around each other, in this rotating reference frame, there are 5 points where the gravity and centripetal forces from these objects are going to balance out. There are 3 of them in a straight line between the objects. In this example, the Sun and Jupiter. They're labeled L1, 2, and 3. Those are what we call metastable points. They aren't entirely stable. You can park there if you do a little bit of work. L4 and L5 are stable Lagrange points. So it's not uncommon for other objects to naturally get trapped at these positions. In the solar system, we often call these Trojan asteroids, and Jupiter has collected thousands of them. So there are these little clouds of asteroids at L4 and L5 leading and trailing Jupiter in its orbit around the sun. These asteroids are truly in orbit around the sun, but in this rotating reference frame, they chart some pretty interesting paths through space. I'm highlighting a couple of them for you here. These sorts of paths are referred to as tadpole orbits. There are other related orbits called horseshoe orbits, but that's probably a story for another day. Now, some of these Trojan asteroids trapped near Jupiter's orbit are interesting targets for planetary scientists because we think they might be leftover fossils from the formation of the planets. So a recently launched mission, the Lucy mission, is on its way out to these clouds of asteroids. It's going to fly through a bunch of them in the late 2020s and early 2030s and show us what these worlds are like. But Jupiter isn't the only planet that has Trojan asteroids. Earth has some Trojan asteroids as well. And just yesterday, one of them was in the news. Our second Trojan asteroid was just confirmed. We now know it's about 1 kilometer or 0.6 of a mile in diameter. Both of our Trojan asteroids orbit our L4 points. So they're leading Earth in its orbit around the sun. And thanks to the more complete data on JPL's servers, I can actually show you their tadpole orbits in 3 dimensions, which is pretty cool. But I do also want to say that Lagrange points aren't just for planets. So, yes, all the planets have Lagrange points in their orbits with the sun, but smaller worlds can have Lagrange points too. Moons can have Lagrange points. Take, for example, here in the Saturn system. One of its moons is especially notable. The moon Tethys actually shares its orbit around Saturn with two other smaller moons. Sometimes call these co-orbital moons. But if I highlight the moon's locations, your brain is probably already connecting the dots, and you can see that these moons are at the L4 and 5 points of the moon Tethys. So these moons, Telesto and Calypso, are Trojan moons. I mean, that's pretty cool. And they aren't even the only ones in the Saturn system. Another one of Saturn's moon, Dione, also has two co-orbital moons, Helene and Polydeuces, and they too are pretty close to the L4 and L5 points in the Saturn Dione system. So you call those Trojan moons as well. I could probably keep finding Trojan moons at farther and farther destinations, but let's get closer to home. Earth's neighborhood is rich with Lagrange points. We have, of course, all 5 Lagrange points in the Earth-Moon system. Now, the Earth-Moon L1 and L3 points don't have a whole lot going on, so we're going to dismiss those pretty quickly. The Earth-Moon L4 and L5 points, no large objects there, but there are some studies that suggest there are clouds of dust trapped at those locations. Kind of neat, I suppose. The Earth-Moon L2 point has proven useful. China has a spacecraft there right now called Qichao. It helps them keep a constant view on the far side of the moon, where they have a lander and a rover. Then there are 2 of the Sun-Earth Lagrange points in our neighborhood, L1 and L2. Remember, those are in a straight line between the Sun and the Earth. And with a little bit of work, with occasional engine burns, they're pretty good places to park orbits. You can actually, park spacecraft. You can actually get spacecraft into orbits around these points in space. They're empty points, but you can orbit around them. The Sun-Earth L1 point, since it's a little bit closer to the sun all the time, that's a good place to, well, watch our closest star, monitor it for big solar flares, coronal mass ejections, monitor space weather. That's pretty important to us here on Earth. And then the Sun-Earth L2 point, because it's a little bit farther from the sun, or always on the opposite side of the sun from the Earth, it's a really good place to do astronomy, and that's what JWST is out there to do. So now that it is in its halo orbit around L2, JWST, from its perspective, can keep the sun, Earth, and moon on one side of it. And because it wants to get its instruments cool, it keeps the sun, Earth, and moon to its back. So a big sun shield there is there to block all the light and heat from all those worlds. And then facing away from the sun, it's got a constant view of the rest of the universe. It's close to the Earth, but it's at a stable point, and it's got a very stable thermal and radiation environment. So L2 might be one of the greatest Lagrange points in the solar system, and definitely in the history of astronomy. And going to be incredibly important to JWST. Its position in space is very special to it. From this point, although it can't point too close to the sun, at any given time, it can see about 35% of the sky, and then as it follows the Earth in its orbit around the sun over the course of a year, it'll be able to cover the entire sky, which I think is pretty cool. In fact, I can highlight for you here in green the part of the sky that it is able to see. This is a bit more impressive here in the dome. So come and visit us sometime. I could show you this in a much more immersive environment. You can see what JWST is able to look at right now. Now, I should also cover, while we're here, what JWST is going to be doing next. It got into space, it got unfolded, it arrived at L2. So the next big sequence of events is, well, now it's here, just waiting for the mirror and instruments to get to their operating temperatures. I briefly talked about Hubble's problems when it was launched into space. So it might really scare you to hear that the primary mirror segments on JWST were purposefully made the wrong shape, but the wrong shape at the temperatures they were here on Earth. Now that they're at L2, they're getting very cold. The low temperatures will help them deform into the correct shape. But JWST's vision still won't be perfect. So each individual mirror segment has little motors behind it, little actuators, and that will help astronomers over the next couple of months get those mirror segments perfectly aligned. You want light reflecting off of each individual mirror segment to fall onto that secondary mirror stationed out in the front. So we'll be taking lots of pictures of the same bright star, moving each individual mirror segment very small distances. I've exaggerated it for this animation. Those motors can move the mirrors at distances equal to about 1/10,000th the width of an average human hair. So these are exacting motions they're going to put these mirror segments through. And once they're all aligned, all of their images are falling directly on the secondary mirror. Then that'll be fed into the instruments, and the telescope will be ready to do science. To put that complex process into words that might make a little more sense to some of us in the current world. Right now, JWST's mirror is in this situation. They've got all the mirrors, but they're in the wrong places. And over the next 5 months or so, the goal is to get them into this situation. So we'll get everything properly positioned, ready to do science. And then it will be off and running with a brand new state-of-the-art infrared observatory. But because there are so many adjustments to make and the mirrors move very slowly, this process is expected to take until June. So I don't have any fancy images from JWST to show you just yet, but I'm sure by midsummer we will be sharing those with you as soon as those are available. In the meantime, and in the last few minutes I have, then let's focus on one other notable feature of JWST. And again, with the Olympics about to start, there's something that we're going to be hearing an awful lot about. It's the pursuit of those gold medals. JWST's mirrors are coated in gold. There's an important reason for that. Gold is an almost perfect reflector of infrared light. So if you're going to gather it and feed it into your scientific instruments that are sensitive to infrared light, you might as well use a perfect reflector. Although the mirror is big, the layer of gold is very thin. Altogether, to coat the mirrors, the mass of gold, the amount of gold used on JWST is roughly equivalent to the mass of a golf ball. So it's not very much. If you've got a couple pieces of gold jewelry at home, you might have more gold in your house than JWST has on all of its mirrors. But a natural question for me to ask would be, well, where did all of that gold come from? You may have heard that heavier elements like gold are created when giant stars reach the end of their lives and they explode as supernovae. If you have a star at least 8 times the mass of its sun, when it exhausts all of the fuel in its core, the core will collapse, the outer layers bounce off of it, releases a huge amount of energy, it goes supernova, and yes, some heavier elements are created. But it turns out that's probably not where most of the gold in the universe, in our jewelry, in the Olympic medals, or on the telescope's mirrors come from. Most of that gold probably comes from a slightly different type of cosmic event, one that I can summarize with the following audio data. Listen carefully, see if you can hear the moment when huge amounts of gold are created. Did anybody catch it? Probably not, because it was buried in the noise. Here's a cleaned up copy that removes the noise. The sound of gold creation, right? That is actually sonification of gravitational wave data collected by the LIGO Observatory in August of 2017. The event that created those gravitational waves was the merger of two neutron stars. Now, neutron stars are left over from smaller supernova explosions. The big supernovae make black holes. So, to get a merger of two neutron stars, you got to have two big stars that explode as supernovae, leave these neutron stars behind. The neutron stars have to be in orbit around each other, and then they eventually merge. And then you create a whole bunch of gold. Sounds like kind of a wild story, but because we captured that gravitational wave data, we've got direct evidence that this is what happens. After those gravitational waves were collected, astronomers quickly went to work on localizing where they had come from in the universe. They were tracked to a galaxy called NGC 4993. And with that information in hand, telescopes all over the planet and in space pointed towards this galaxy to observe the aftermath of this neutron star merger. Here are images from the Hubble Space Telescope. They actually show the afterglow from this kilonova event. That's what these explosions are referred to as. But as we've already seen, there are a lot of kinds of light that the universe can use to communicate with us. So telescopes across the electromagnetic spectrum were used to observe the aftermath of this neutron star merger. I know these labels get really small, so I will tell you that on the bottom left there, those are X-ray observations in the little inset window. And at the top, I've got ultraviolet observations. Just like infrared light is incredibly valuable, all these other kinds of light are informative as well. So by analyzing all of these colors of light that we have at our disposal, you can see what's going on in these kilonova explosions, and you find that most of the gold in the universe on the periodic table, it's kind of in the middle, fifth row down, number 79. Most of that square is colored yellow in this version because showing us that most of the gold out there comes from neutron star mergers. That seems like a pretty fantastic story on its own, but we actually aren't done with getting the gold for our jewelry and Olympic medals and JWST's mirrors. You have to get from the gold that's just out there in the universe to the gold that we have access to here on Earth. With the universe enriched in these heavy elements, the cloud that the solar system formed out of would have had some gold in it. So the Earth would have formed with a little bit of gold, but we shouldn't really have access to any of Earth's original gold, or at least only minuscule amounts of it. See, our planet is, well, it's a little bit like an onion. It's got layers, and we're going to peel away some of the layers here. So first thing we'll do is get rid of the atmosphere of the Earth. And then I will get rid of Earth's oceans as well. This reveals the outermost solid layer of the Earth, the rocky crust that we live on, and the rocky crust that we dig all of our precious metals out of. It's not very thick, but we don't have access to any of the layers down below it. Below the crust, we have the mantle. It's split into the upper and lower mantle. A couple of things to know about the mantle. It's solid rock, so similar ingredients to what we have here on the crust, but it's pretty warm, so it does move over geologic timescales. It behaves more like a fluid. Down below the mantle, we have Earth's core. There's an outer and inner core. The outer core is molten. The inner core is thought to be largely solid, and the core is made primarily of metal, mostly iron and nickel metal, and other iron-loving elements like gold. Most of Earth's original gold should be here at the core because when Earth was first forming, the whole thing was molten. And so then we have to think about, well, why things sink and float, the basic rules of buoyancy. Take something heavy like, I don't know, a chunk of gold, drop it in a less dense fluid like water or molten rock, the gold is going to sink. So pretty much all of Earth's original gold should be here in the core. So how did we get gold in the crust that we could mine out and use to make things like telescope mirrors? Well, imagine if we had some cores of former planets, maybe other protoplanets were forming early in the history of the solar system. Through big collisions, maybe their crusts and mantles got stripped away, leaving the cores behind. We could have solid chunks of iron, nickel, and more importantly, gold drifting through the solar system. Now, if these chunks of metal were to hit the Earth later on, some of that metal would get deposited in the crust of our planet, and that would be more readily available to us. That sounds almost as fantastic as these merging neutron stars making the gold in the first place, but that could be the source of all the gold we have on Earth, and I can show you why in a shortened version of our ongoing series, Better Known Asteroid. Today, a twofer, 1986 DA and 2016 ED85. These are both near-Earth asteroids, and to really bring it back home, using infrared observations, infrared spectroscopy, in fact, where the light reflecting off these asteroids is split into its component colors. You can see that their spectra are these sloped but otherwise featureless lines. That is a hallmark of what we call M-class asteroids. The M here stands for, you guessed it, metals. The largest M-class asteroid is named Psyche. It's in the main asteroid belt, and with all of their spectra on the screen together, you can see that they are, well, pretty similar. So all of these asteroids could be chunks of metal. Psyche may be the intact core of a protoplanet, or at least largely intact. The smaller near-Earth asteroids here could be fragments that were broken off of a similar large M-class asteroid. It's kind of a fantastic story too, but we're going to get a better look at Psyche in the not too distant future. Later this year, the Psyche mission is scheduled to launch. It's headed to the asteroid Psyche. And with Psyche, we'll be able to get to what geologists might call ground truth data. Instead of just the remote sensing observations that we're used to in astronomy, we're going to have a spacecraft right there at the asteroid, taking up close pictures, analyzing the ingredients that make up the rocks on the surface of Psyche, and that'll help us either confirm or refute this theory that the gold and other precious metals in Earth's crust may have been delivered by large asteroid impacts. As for Psyche itself, it is pretty big. If it is the exposed core of a protoplanet, that protoplanet must have been much smaller than Earth. Psyche's long dimension, its equatorial diameter, is a little bit bigger than Virginia's north-south width. So that's the asteroid Psyche, and the spacecraft Psyche will arrive there after about 3.5 years journey. So that'll be in late 2025, early 2026. So we've got that to look forward to. We can see if this asteroid is the source of heavy metals in Earth's crust, or asteroids like it. Maybe we'll finally understand where the gold to make mirrors like JWSTs come from. And as usual with my shows, no matter where we start, it all comes back to asteroids. But there you go. There's a look at JWST, its current status, and some of its most notable features. And with that, Jim, if we've got any questions, I'm happy to address those.
All right, Justin, thanks a lot. So if we could real quick circle back to the moons of Saturn. Now, what's the current count on how many moons Saturn has?
83 moons have been found so far, but the 83rd, the newest one to be discovered just in the last, or confirmed at least, just in the last couple of months, comes from a team that found dozens of other candidates. And if more of those get confirmed, it suggests there could be hundreds of moons there.
All right, great. So with the length of time it took to develop the JWST, what does NASA have in the works for the next space telescope? Do they have anything on the books that we know of?
Yeah, there are a couple of more space telescopes coming up. There is one called, well, it'll be named after Nancy Grace Roman, the woman that I mentioned who really guided Hubble through its development. That's going to be another infrared telescope, but its cameras will be designed to take pictures of much larger patches of the sky all at once. It's going to be a big survey telescope. That one is still a few years out, but it's in its final phases of planning and development. There's another big planning process that kind of wrapped up over the last year. It's called the Decadal Survey, and this is what really drives priorities in funding major space projects like JWST and other space telescopes. And one of the recommendations from the newest Decadal Survey was another even larger space telescope. Would probably be a similar design to JWST, but even bigger. They kind of suggested merging two ideas that are out there, and so I can't tell you exactly what form it'll take. But as the name suggests, that's at least a decade from coming to fruition.
Okay, so it seems like every time I read an astronomy news story with some interesting finding, there's always the sentence. It's hoped that the James Webb Space Telescope can shed some more light on this information. So I would imagine that the JWST's got quite a full dance card. What does NASA intend to kind of look at first?
There is a whole list of observations that have already been planned. And let me see, I can actually, yeah, for anyone that really wants to dive into the answer to that question, here's a list in the chat of what's called the guaranteed time observations that are planned for the first year or so of JWST's observations. So they're going to study everything from galaxies to newly forming stars to these very cool objects that are kind of on the boundary between planets and stars called brown dwarfs. They're going to study a bunch of things here in our solar system too, the gas giant planets, Kuiper belt objects out beyond Neptune. Yeah, they're really going to observe pretty much everything the universe has to offer and see how Webb sees them.
All right. So do you have any information on? We had the question: was the JWST assembled in Maryland? Where was this thing put together?
Yeah, a lot of the assembly of the telescope was done at Goddard Space Flight Center up in Maryland. The final assembly then was over in California at Northrop Grumman's headquarters. But yeah, you can definitely find a lot of pictures of the mirrors when it was in the clean room up at Goddard, and you go into the observing deck for about a year there as they were doing that assembly and actually see the mirror there.
Is there any question that you personally are really looking forward to seeing answered from JWST data?
Oh man, one of the most profound might be when we start looking at those extrasolar planets, those planets orbiting other stars. One thing that JWST will be able to do is actually use spectroscopy to study the gases that make up their atmospheres. And if you're kind of familiar with the way life has altered Earth's atmosphere, you know that there are markers like oxygen and methane in our atmosphere. They're only here in large amounts because life exists. So if JWST is able to find a kind of smallish rocky planet that has an oxygen-rich atmosphere, about the only explanation we have for that right now. Is life. So, I mean, yeah, looking at exoplanet atmospheres, that's what I'm looking forward to the most.
All right, we had another Saturn question. You have another Saturn question.
And of course, yeah.
We had a question about the composition of Saturn's ring.
The rings, so the rings that we can see with our own eyes, those are just chunks of rock and little bits of dust and ice. Lots of ice. That's why they're so reflective and easy to see. I mentioned another ring, the one that the Spitzer Space Telescope discovered. That is largely dust, and it's very dark colored dust. So we don't see it in visible light because it's so dark. It's warmed up by sunlight. It releases a little bit of heat. That's why it's visible in infrared light. And that particular ring is sometimes called the Phoebe ring because it may be dust that's blasted off of the surface of one of the smaller moons named Phoebe. And that moon itself is thought to be a captured Kuiper belt object. So this thing formed much farther from the sun wandered closer to the sun at some point in the last 4.5 billion years, got close enough to Saturn, that was captured by Saturn's gravity, became a moon, and then impacts by other smaller objects over the last few billion years has formed this dusty ring, which I think is pretty cool too.
Yeah, I'd like to add for everyone in the audience, if you have not had a chance to come to a live astronomy show in the Dome, that is a great way to really get an amazing view of Saturn's rings, Saturn's moons. Justin does a really great job of these tours of the solar system. And if you have not checked out the Dome, you should definitely come by the museum and do that. So, any other questions for Justin? Here we go. So, Justin, where will the first pictures taken by JWST be available for viewing? Where is a good place or website where the public will be able to see the available data?
NASA is very excited about this because of the length of time that it took to develop JWST and the fairly famous cost overruns and launch delays. They really want to show off that it was worth the wait. So I dare say you will not be able to miss the first images when they are released. I'm sure they're going to be all over the news, going to be all over social media. They will be on NASA's front page. We'll definitely have them for you. I mean, I definitely recommend coming to see them projected over the quarter-acre dome. But yeah, the very first images are going to be everywhere, so you won't be able to miss them. But you can also just head to nasa.gov. When those are released in late June, early July, they'll be there as well.
All right, Justin, looks like we're about out of time for today. So thank you very much for joining us. Excellent presentation, as always.
Thank
Always
you.
love to have you on. Thanks to everyone in the audience for joining us today. So please join us on Wednesday, February 16th at noon for Virginia STEM Board, Unifying Virginia's STEM Efforts. So if you're interested at all in the state of STEM education in Virginia, you'll definitely want to catch that. That is going to be presented by Mr. Chuck English. He is the Virginia STEM coordinator. You can register for next week's talk at smv.org. Each talk is free to attend and is open to the first 300 registrants. Thank you again for joining us today. Until next week, stay safe and stay curious. Thank you all for being here today.